Hello friends, once again I am here to discuss a new topic in our ongoing series on AI and pharmaceutical sciences. In this video, we will talk about a very breakthrough, highly quoted, highly cited, referred and used research article in the current time. How to use deep learning models belonging to autoencoder category for de novo drug designing. Deep learning is a subtype of machine learning, which in turn is a subtype of AI, that is artificial intelligence. De novo drug design means to design entirely a novel, new drug-like structure from scratch in silico or in screen. So if you do this exercise through AI, it is called deep generative model for de novo drug designing. So I go ahead with this paper. It is a breakthrough research article, and I have taken all the language and sentences as such from this paper without any modification. So I am thankful to entire researchers and publishing house. So I go ahead with this paper. The title is Automatic Chemical Design Using a Data-Driven Continuous Representation of Molecule. So we will talk about the meaning of data-driven continuous representation in coming slides. So the authors are Rafael Gomez, Bombrelli, Jennifer Weil, David, Jose Benjamin, Dennis George, and other Ellen Espruzzi-Guzik. So these are the authors of this paper, and I have seen this paper around 2 months back, and you see the article views. More than 80,000 people have viewed this article, and I mean around 50 times I have seen this article, and citations are 792 in 3 years. Very historical, novel, breakthrough, pioneer work they have done, and for many years to come this paper will be cited as historical paper, and definitely very easy to understand step by step tutorial fashion paper I have come across. So I'm using this paper to explain you the application of AI, that is deep learning, in de novo drug designing. So he is the one of the author, Rafael Gomez Bombrelli. His very few articles, research article, review article he has written, and he is very active in this domain. I have seen his biodata profile, and he has been a regular face when it comes to updates regarding AI, specifically in generative type of deep learning models for making use of AI in drug discovery through de novo molecule synthesis route. You may watch his videos in various blogs and review articles and research articles on internet. Presently, Dr. Raphael is assistant professor in material processing, Jeffrey Cha career development side chair in engineering at world famous MIT University. Other famous authors are Ellen Esper Guzik. He has also written few papers. That paper you may also you may see on the net. So exactly what they have done. So before you watch this tutorial video as part of my course, I request you to go through the basics of deep learning, machine learning, and specifically what is the meaning and basic structure and use and function and the working style of autoencoders, because the entire paper or the research revolves around autoencoder of type variational, that is VAE. So if you don't know that particular type of autoencoder, it is not interesting for you. So I request you to go through those videos early first, then watch this video. In this paper, what they have summarized: recent advances in machine learning have resulted in powerful probabilistic generative models that, after being trained on real examples, are able to produce realistic synthetic samples. It means there are few deep learning models like autoencoder and GANs, that is generative adversarial network. This type of deep neural model, they can be trained using hundreds of thousands of input images, for example. Then after training and testing and validation, the same deep learning model can be used to generate new type of structures which may or may not be similar to the trained input samples. Now the such type of work has been cited by many authors. but very few research article, review article are there in public domain or otherwise, which can be which can show the promising applications of AI. But scientists are working continuously to use this technology, that is to generate samples, images, I mean to generate molecules based on input molecule during training. But history will be I mean it is not it is not difficult now. Lot many work is going on, and very few we will come to know that few companies got success in developing model, I mean the drugs through generative models. Now such models usually also produce low dimensional continuous representation of the data being modeled, allowing interpolation or analogical reasoning for natural images, text, speech and music. So this type of model convert your input data into very low dimensional space, or in a hidden pattern they convert your entire input molecule or input picture or input sentence for that matter into very less space area, that is called hidden space or latent space. Everything is not explicitly shown, it is called latent space. These researchers applied such generative models to chemical design using a pair of deep network trained as an autoencoder to convert molecules represented as smiles strings into a continuous vector representation. We all know we have to convert molecules into machine readable format through various molecular representation techniques. One such technique is smiles, that is simplified molecular input line entry system. So smiles are utilized by this author also to train the autoencoder. So they first converted their molecule into smiles, and smiles have been converted into continuous vector representation through encoder. What is the meaning of continuous vector representation? There are continuous vectors. By changing or by tweaking those vector values, you can pick out different type of molecule from the latent space, and you can convert them into convert those vector into smile, and finally from smiles to molecule. So basically this method of converting from a molecular representation to a continuous vector representation could be applied to any molecular representation, including chemical fingerprints, convolutional neural network, on graph, similar graph convolutions and Coulomb matrix. So here I will elaborate further. So what the meaning of this molecular representation means: to convert your input chemical or drug molecule into machine readable format through various available softwares which can convert your molecule into different representation. For example, a Coulomb matrix, or for that matter smiles or fingerprint or other type of vectors, or convolutional graph neural network, which is in current fashion now. So what is the meaning of continuous vector representation? We all know vector means a mathematical system to present your input data feature. And what is continuous? In those vectors there are continuous readings in terms of numbers, and those numbers can be picked up by decoder, which is a part of autoencoder, and decoder will convert those picked up sample values, that is from vector, into smiles, and again smile will be changed into the molecule. This is the meaning of continuous vector representation. And this particular feature, that is continuous vector representation of the molecule, is missing in standard or general or simple or vanilla autoencoder. So here there was need of a system which can have the continuous vector representation of molecule after training through input dataset. And here comes the role of variational autoencoder. So in this paper, researchers chose to use smiles representation because this representation can be readily converted into a molecule. Variational autoencoder with recurrent neural network. So again, I would request you to watch again earlier video in my unit number 2, where we have discussed about deep learning models, that is recurrent neural network, convolutional neural network, that is CNN, and all those models, encoding, decoding, autoencoder in detail. In a elaborative manner, we have discussed in unit 2 what is the meaning of recurrent neural network, what is the meaning of convolutional neural network, what is the meaning of graph convolutional neural network, what is the meaning of convolutional graph network, what is the meaning of autoencoder, what is the meaning of variational autoencoder, because these are the basic models at present which are being used to see the full fruits of generative models. What is the meaning of generative model? To use machine learning techniques to generate your own sample, to generate your own products. For example, you have shown your image to the deep learning model. So model will learn the basic features of your face, and based on those basic features of your face, based on the pixel criteria, it will generate thousands of images which will be like your image, or there will be some modification or tweaking based on how you are playing with those continuous vector representation of your image in the latent space. What is the meaning of latent space? The hidden space, or the I mean the area or the space where lot many molecules are present in the hidden or in the dormant fashion, in small compressed fashion. It is called latent space. So variational autoencoder with recurrent neural network encoding decoding were proposed by Baumann in the context of written English sentences, and they followed their approach closely. So the researchers have followed the approach given by Baumann and team for generating English sentences based on natural language processing through sequence to sequence or sequence to sequence arrangement of the letters and sentences or the words. To use the power of recent advances in sequence to sequence autoencoders for modeling text, this team used to SMILE representation, a commonly used text encoding for organic molecule. Here what they want to say, for example, a sentence is there, I am going. So the, because through natural language processing, the system knows that if I is there, going is there, so there might be chances of am or was. This is called sequence to sequence learning or sequence to sequence autoencoders application. Here in the similar way, SMILE is a way to represent molecule, and we have to train the model through, for example, through recurrent neural network to understand the grammar, that is the chemical grammar of the various molecule. So we all know RNN, that is recurrent neural network, is used to train the deep learning model for understanding the presentation or the arrangement of various type of sentences or grammar of a sequential input data. Using this new continuous vector valued representation, they experimented with the use of continuous optimization to produce novel compounds. What is continuous optimization? Suppose from continuous vector value, from continuous vector representation from the latent space, they picked up one data point and they are not finding its value similar to a drug-like molecule. Then they will further optimize by tweaking the errors, I mean the weights and biases, to produce novel compound. They trained the autoencoder jointly on a property prediction task by adding a multi-layer perceptron that predicts property. So here they have done two things. First, they have trained a deep learning model, that is variational autoencoder model, to produce various smiles and molecule through latent space. Second task they have done, they optimize or continuously change or play with the latent space so that the molecules will be generated by a decoder which will be like drug like molecule. So constantly they were changing the log p value and all those Lipinski's parameter in the molecules or the continuous vector present in the latent representation. So for this they attach one property predictor type of machine learning model. So they are calling it joint property predictor model. So they are doing two things: to convert molecule from latent space to the uh, again a chemically feasible SMILE strings, and finally to molecule. And second task they have done is to optimize those SMILE strings in the continuous vector representation in the latent space, so that they will have some predicted property which were shown to the machine learning model during training through various samples, through various data sets. Then they examined the effects that joint training had on the latent space and tested optimization in this latent space for new molecules that optimize desired properties. So how they have done it? To enable molecular design, the chemical structures encoded in the continuous representation of the autoencoder need to be correlated with the targeted property. So they mapped representation with the target property, for example Lipinski's parameter. Because if we see, we can get hundreds of smiles, but there are two drawbacks. If smiles are not chemical friendly, it means those structures are not within, they are not falling within the rules of chemistry, or they cannot be synthesized in the laboratory, or they can be designed in the laboratory, they follow chemistry rules, but they don't have the property, for example Lipinski's property, which are the basic need for a molecule to be called drug molecule. So continuously they were tweaking the continuous vector so that the smile should be chemically I mean the smile should be chemistry friendly, and they should be synthesized in the laboratory, and they should have some property like drug like property, the log p value, number of hydrogen donor and donor, number of hydrogen donors and acceptor. So all these properties continuously they were optimizing or tweaking in the latent vector to make only drug like smile. Therefore they added a model to the autoencoder that predicts the properties from the latent space representation. This autoencoder was then trained jointly on the reconstruction task and the property prediction task. What is the reconstruction? What they are telling here, jointly means for two purpose. Number A means reconstruction. From latent space, you have to, from this continuous latent representation, you have to reconstruct the smiles which are valid as per RDKit library. Then property prediction. What is the property of those smiles? Property should be like the property should be matchable with the property of the training molecule. Otherwise there is no use of generating hundreds or thousands of smile strings. So to propose promising new candidate molecule, one can start the latent vector of an encoder molecule and then move in the direction most likely to improve the desired attributes. I will tell you through the images given in this video, which I have taken from the original research article. So now what you have seen, they have just converted sample training molecule into smile string, and directly through smile strings they have tried to make a generative deep learning model which can produce drug like structures. So without telling anything about the protein structure, without telling anything about the chemical nature of the molecule, just by showing them chemical strings, the model was sufficient to learn, to understand the grammar of a small molecule, and then it generated the molecule. It is very beautiful. No detail about the receptor or the proteins, no 2D 3D structure, only smile strings which were very easy to handle were used to train the deep learning model. So what they are telling, despite the fact that the VA is trained purely on the smile strings independently of chemical properties, it is able to generate realistic looking molecules whose features follow the intrinsic distribution of training data. So they got success in producing or generating molecules which are realistic, and they follow the intrinsic distribution of the training data. Suppose they have trained the autoencoder using 10,000 small molecule. So all the generated molecule were conforming to the properties of those training molecule. It means your variational autoencoder model was sufficient to understand and to learn and to retain the most important features of the training molecule. This is the beauty. What is the meaning of most important feature? Only those features which are responsible for making those molecule drug like. So this is the beauty of this autoencoder architect. It learn only the required properties, and this is the job of encoder. While encoding the compound, it learn only latent features, only the required features. For unconstrained optimization, in the latent space to work, points in the latent space must decode into valid smile. It is very important, and this slide separates the variational autoencoder from the general or vanilla or standard or simple or basic autoencoder, which does only one job: to encode the molecule into latent space, and from latent space the decoder convert back into the original molecule, which may be similar to original molecule. But you have to generate more and more sample from the latent space. For that, you have to use variational autoencoder. So what is the important feature? For unlimited optimization in the latent space, points in the latent space must decode into valid smile. The beauty of latent space is that all the similar data points or similar structures are close to each other in latent space, and those structures which are not similar, they are different or apart in the space from those similar molecule, right? Number two, the property must be that all the data point in the latent space must be able to be decoded into valid smile. What is the meaning of valid? They should be chemically feasible, right? So without this feature, latent space by the autoencoder may be sparse. Means in latent space there will be only 2 points and 3 points will be far away. No, it is not the purpose of latent space. Latent space should have all the molecule which are alike or identical or similar to each other. They should be in one cluster, they should be in one vicinity, and others should be away from those. So if there are sparse or gap in the latent space, they are called dead areas, and they will decode into invalid smile. The meaning of smiles which are valid means they can be converted into a chemically friendly molecule. So to help ensure that points in the latent space correspond to valid realistic molecules only, the researcher in this team chose to use a variational autoencoder. Autoencoders refer to architectures that were traditionally used for dimensionality reduction and trained in an unsupervised manner. As we already seen in earlier video, what is the meaning of autoencoder? Autoencoders are the group of two neural network, encoder and decoder. Encoder converts your input molecule into low dimensional space or in the compressed fashion, and decoder again convert the data from those latent space which are the combinations of various molecules in the compressed fashion to the original molecule in an unsupervised manner. The main idea in this autoencoder is that they learn to preserve the essential part of the data and remove the non-essential part. The essential part means those parts which make the molecule a particular molecule. They process a new family of methods for exploring chemical space based on continuous encodings of molecule, as we have discussed. These methods eliminate the need to handcraft libraries of compounds and allow a new type of directed gradient based search through chemical space. In their autoencoder model, researchers observed high fidelity in reconstruction of smile strings and the ability to capture characteristic features. Here are two things: high fidelity. Your smile string, which is a way to represent chemical structure, should have 2 things: high fidelity, and the smile should be able to capture the characteristic features of the training molecule. The meaning of high fidelity means they should be able to convert into chemical structures through decoder, and they should be able to follow chemistry rules, and they should represent some basic features they have learned from the training data set. Otherwise, there is no use of training the machine learning model. The autoencoder exhibited good predictive power when training jointly with a property prediction task. As I told you, our purpose is not only to generate molecule through latent space, but to generate those molecules which are having some physical and chemical properties resembling to the training data set, and these properties are the yardstick to measure whether your generated molecules are drug like or not. Otherwise, you are just producing n number of molecules which may or may not be friendly in terms of chemistry rules, and they may or may not be having the physical chemical properties which are the essential yardsticks for a molecule to be called drug molecule. When converting a molecules from a latent representation to a molecule, the decoder molecule samples a string from the probability distribution over characters in each position generated by its final layer. Here the meaning is when the decoder converts or pick up a point from or vector from latent space, then it checks all the probability distribution. What should be the next token or the next structure, whether it should be C or a bracket or double bond or triple bond or hydrogen or nitrogen, aromatic or aliphatic, whatever. This is called picking off of the proper token or number or symbol through probability distribution. And this is the beauty of latent representation or latent space in case of variational autoencoder, which is missing, massively missing or heavily missing in vanilla autoencoder, and which is not the job of vanilla autoencoder. So that there is use of variational autoencoder. As such, multiple smiles strings can be possible from a single latent space, and therefore there is use of RDKit to validate, to check the chemical structure of output molecules and discard invalid smiles. Two autoencoder systems were trained, one with 1,08,000 molecules from the QM9 dataset and other from a ZINC database. So with joint training for property prediction, the distribution of molecule in the latent space is organized by property values. It means, very important, it means in the latent space all those molecules which may or may not be chemically similar, but they are having same physicochemical property. Such molecules were placed automatically by the autoencoder in close proximity, in close vicinity. So whenever you will pick a molecule, for example, from, I will tell you in next slide what is the meaning of this sentence. Remember it. The latent space generated by autoencoders jointly trained with the property prediction shows in the distribution of molecule a gradient by property values. Molecule with high values are located in one region and molecules with low value are in another. I mean, there is no mixing up in the latent space, and this is the main feature of latent space. Autoencoders that were trained without the property prediction task do not show a discernible pattern. It is important why there was need for two type of model, one for generating the smile, another was to optimize the latent space, so that the only those smiles will be generated usually which are having some drug like property. This is the beauty. So if you don't use joint property predictor, if you don't attach a property predictor with your generator, then you will get various smiles which will not follow the rules of chemistry, or which may not represent the true feature or the essence of training samples. To create a smoother landscape to perform property optimization, the researchers team used a Gaussian process to model the property predictor model. So while training this model for training the Gaussian process, the team used 2000 molecules, because until you are showing different types of molecule, that is input sample to the machine, it will not learn a proper distribution of the variety of the input features. So using this model, team optimized in latent space to find a molecule that maximize the objective. What is the objective? The objective of this training was to produce the drug-like molecule which are having the quantitative estimation of drug likeness, and which are having the synthetic accessibility score. Means, to make those molecule which are having the drug-like property, at the same time they should be able to be synthesized in the laboratory. So how they started? To provide the greatest challenge and to make the robust optimizer, to develop a robust machine learning model, the team started with the molecule from ZINC database that had an objective score of in the 10%. So they started with one of the minimum optimum objective score, and from that score they continuously they optimize through gradient optimization continuously by number of epoch and learning rates. They got success to get a drug like molecule. So they start from very low level of drug likeness, and they went to high level of drug likeness. So here now we come to the structure. Here you see this is your drug molecule, for example. Sorry, this only this one, and this is your smile string. Now this is encoder having various layers of neural network. This encoder will convert this molecule into, this is your latent space, and various molecules will be this is lot many latent representations of your input molecule will be there. Suppose this particular area is there, so all the latent representation in this area will be more similar in nature, either in chemistry or in physicochemical property, compared to those molecules which are present in this cluster. Ultimately this entire is called latent representation or the latent space. Latent means some hidden features. It is a dormant structure, a compressed way to represent your high dimensional data into low dimensional data. Now this is latent representation, this is decoder. So decoder will decode the molecule from this latent structure to this structure. This is simple, this simple and autoencoder. Now another structure, this is the structure I have taken from the paper. So this is your smile string encoder, and this will convert into, this is your latent space. So lot many samples are there, molecule number 1, molecule number 2, molecule number 3. So for example, if you are moving from this left corner to right corner, so this will be like more drug likeness. For example, this structure is for example having very low or poor synthetic accessibility score or poor drug likeness property. So as in when you will go ahead in this direction, you will get more and more molecules which are having more drug likeness property. So how to move in this direction? It is decided by the property predictor type of machine learning model. So it is called joint property predictor molecule, right? So this is another same example in different pattern. Your structure you have changed into machine readable format. It is called smile. This is smile. This is your encoder. The job of encoder is to convert your smile into this latent representation. This is called continuous molecular representation, which is missing in the simple autoencoder. It is called latent space. Huge huge data set is there. So for example, all the molecule in this particular area will be similar. It is similar. So it is different. It is different. So you understand in this way manner. This is red color. So all the molecule in this red area will be having some common features. So this is property predictor. You will pick this example and you will check the property. If it is okay, go ahead. If it is not okay, send it is back here and optimize this particular the standard deviation and average mean vector, and again check it. So it is continuous generation of molecule and continuous optimization. This is the property of variational autoencoder, right? Same what I tell you, just the same. Another, so yes, now suppose you have trained a autoencoder to study this particular molecule ibuprofen, right? So when you will pick a molecule from latent space which is closer to ibuprofen, so you will get this type of structure, this one, this one, this one. So they all are having some features, at least chemically or morphologically, phenotypically, these features are identical to ibuprofen, but they may or may not be drug likeness. So how it is happening? Suppose this is the latent space and here is your ibuprofen, this one. And if you picked one molecule from this area, and this area, so all these three molecules will be identical or somewhat similar to ibuprofen, because in latent space the beauty is that all the similar structures are placed together in close proximity, right? So this is the way to represent the probability distribution. So all these structure will have some common features. This particular normal distribution pattern shows that your latent space is identical or your latent space is standard. Now as you move from this ibuprofen to this direction, you are getting more and more molecule which are more and more different from ibuprofen. So molecule which are in close proximity are these three molecule, then they are less closer, further closer, right? So these are the molecule which may be tested from viewpoint of properties in like ibuprofen, right? So another example is, this is your query compound. For example, this is your query compound which is having zero distance. Now this is the molecule which is very close, identical to query molecule. So the distance is 1.30. This is the molecule which is 1.30 distance away from this query compound. Query compound is having 0 because it is standard, no distance. And again, if talk about this one, it is 13.29 units away from this compound. So this all you can see using various graph in your in your system based on autoencoder. This is the beauty of variational autoencoder, which permits you to design different molecules, not only design but to check whether they are chemically friendly or not, whether they are having some physical and chemical properties which make them drug likeness or not. This is the beauty, right? So another this is the last point, I think. Yes, this one. I mean by the same group of authors, in their supporting data I came across, they find all the molecule which is similar to the query compound in the latent space. So this is the structure of aspirin. They give aspirin. So title, what is the title? Molecules decoded from the randomly sampled points in the latent space of a variational autoencoder near to a given molecule, and the given molecule is aspirin. From the aspirin vicinity, they found tens of molecule, so they are somewhat identical to the molecule of aspirin. So what is the learning message here? Without much effort, just make an autoencoder of variational type through joint property predictor. You make the optimum latent space and get various type of product, I mean the samples which are generated by machine. You have not done it. So it is called a de novo drug designing through variational autoencoder by continuously optimizing latent space through gradient optimization type of statistical treatment. So one of the most exhaustive video I have finished in this course, and this is the future of entire drug discovery. Note down the words of mine. In the coming years, 2 3 4 years, all the drug pharma companies will shift to this type of de novo type of drug discovery through deep learning generative models. Thank you very much.